kids! Today we're going to learn about stars. You want to learn about stars, don't you? I said you want to learn about stars, don't you? Hi, I'm Erika.
And I'm Christina, and we will be your hosts for today's episode of
Dealing with Atoms. Not this kind of dealing.
Ugh, I can't stand Adam.
Today, we will guide you all through the formation of stars, featuring our guest, Star.
I'm a star.
Not that kind of star. Before their lifetime, stars start out as nebulas, which are composed of clouds of dust and atoms.
Next, the dust and atoms will be pulled together by gravity, and under the right conditions, they will form a protostar.
Then, fusion begins. This will lead to the protostar and to the transformation of either an average star or a massive star. First, we're going to look at the life cycle of an average star.
This is an average star in its main sequence of life, similar to our sun.
A star will stay in the main sequence as long as it still has hydrogen to fuse into helium. The main sequence is the longest part of a star's life.
As the main sequence star continues to age, it will decrease in luminosity and temperature, and soon it will run out of hydrogen to fuse. When this happens, the star will start fusing helium and will start expanding until it becomes a red giant.
As red giants continue to fuse heavier and heavier elements, the force of fusion pushing out on the star's mass begins to outweigh the force of the star's gravity.
When this imbalance is achieved, the star will start shedding its outer layers, also known as the planetary nebula. The release of the planetary nebula is a beautiful and awe-inspiring sight. After the planetary nebula has been released, the remaining core of the star will compact into a white dwarf, which will eventually cool down and stop shining.
This will result in a dead black dwarf.
The path of a more massive star starts similar to the path of an average star, but ends quite differently.
Once the star's hydrogen runs out, it cools and expands much like an average star would, but due to its extreme size, it is called a red supergiant. The star's gargantuan mass pulls the matter of the star inward with the same amount of force, reaching a balance.
When a red supergiant begins fusing iron, it can no longer fuse heavier elements. So gravity no longer has to contend with the force of the fusion and cause the iron core to collapse in on itself. The result is a supernova explosion.
Yeah.
The force of the supernova blasts the star's outer layers into space. For an instant, the supernova shines brighter than the entire galaxy.
Sometimes the core survives the supernova, and depending on the mass of the remaining core, one of two things can happen. In their last stage of life, stars can either turn into a black hole or a neutron star.
After the star experiences a supernova explosion, if the core survives and is massive enough, the force of gravity is so strong that it results in a black hole. Once the black hole is formed, we cannot actually see it due to the fact that its gravitational pull is so strong, not even light can escape it. It sucks up everything within its vicinity. Adam, shut up!
As Christina was saying, we can't see them because they suck up light. However, we can see the effects of strong gravitational pull on surrounding stars and galaxies. Adam, stop it!
Great job, Adam. Now you made the power go out.
Now we have to switch sets. I swear I am going to kill you. A typical neutron star is smaller than our sun, but has a mass 3 times of it. The force of gravity between the particles of a neutron star, which are the protons and electrons, are compacted into neutrons since the gravity is so great. The remaining mass of the star begins to spin very fast, and without the force of fusion to bounce the star, all of its mass is compacted into an extremely small space. Thank you for exploring with us on today's episode of Dealing with Atoms.
We hope to see you next time.
Bye!
That's a wrap. Tacos?
Yeah, man, let's go! Adam's so annoying.
Oh my gosh, I can't even stand him.
Ugh, what happened? Why is it so dark in here? Erika? Christina? Guys? Not funny, guys! No! Somebody
Okay,
help-
done.
Next, under the right conditions, wow.
Let's try that again.
Wait.
It looks right.
Officially, you have to make bloopers.